Unit 3 is talking about chemical names. As we can see, it's a very small section in our book. And again, the reason why is because in our book is using a general chemistry book, and therefore in a general chemistry class, naming is a very small portion of what is covered in a general chemistry course, because general chemistry courses are going under the impression you've already had a lot of this. Naming chemical compounds is based on learning the rules set forth by the IUPAC, which stands for the International Union of Pure and Applied Chemistry. I can't agree with your textbook more. It is super important to learn the system. There are some alternative methods in which some people do naming, and it's important that we understand that that is not the route that we will take on these, and we will ask that you learn the methods and the rules set forth by the IUPAC. And that is why some of the answers in class homework are not easily found on the Google, because they don't follow the rules. We are going to want you to learn how to name based on the rules. Sorry, the easiest naming that we cover, some of it has already been covered, and that is that of a formula unit. And that is the smallest individual unit of a material. Basically saying the majority of the periodic table, the elements that we find them, their symbol is basically the formula unit. So if you look on a newer periodic table, there would be 118 elements on the periodic table. 111 of them, the symbol is the formula unit, and back and forth. So the symbol equals their name. There is only 7 of them that are considered to be what are called diatomics. These are molecules that when we say their name, we need to think of them as they are written with these 2's there. That is an important part of it. When we talk about nitrogen and oxygen from here on out, you need to think of it as a diatomic molecule, meaning N2 or O2. If I needed to talk about, say, oxygen, the element itself, I would actually say elemental oxygen, so that we were only talking about just the O. From here on out, when I say something is burned in air, that means it's burned using O2. If it's burned or completely oxidized, it's O2. When I say chlorine gas is added, that means Cl2. These are the diatomics. You need to have them memorized. We have methods in which we can use to memorize them. The methods that we have to do that is, again, H, Noth, and then down. Utilizing our H, Noth, and down is the method that we use. So H, Noth, and down. Or we can also use the method draw a 7 starting at 7. So if I draw a 7 starting at element number 7, that will give me nitrogen, oxygen, fluorine, chlorine, bromine, and iodine. So whatever method you use to write out the diatomics is the one that would be best for you. I prefer H down after a student had told me that, but draw a 7 starting at 7 was the one that I came up with when I was a chemistry student back in the day. For covalent molecular compounds, we have a different way, and you have to be able to know where certain elements are. Meaning, if you need to be able to identify whether or not you have a non-metal or metalloid versus a metal. All covalent molecular compounds, or sometimes just called covalent compounds, always are going to start with a non-metal. So when we look at our non-metals, we can see that all of these compounds start with a non-metal. They also have another non-metal attached to them in some manner. So covalent bonds are held together by sharing. We'll talk more about how they bond in the next unit or a little bit later. However, it is kind of there. We do need to understand that it is through the sharing of the electrons to achieve their octet. But the biggest thing that students need to do is be able to identify your nonmetals. So if you're looking at a compound and it starts with a nonmetal, that should be the trigger in your brain that says, ooh, covalent compound. Or binary compound, whatever you want to call it. If it's followed, and it usually is going to be followed up by a non-metal as well. So you have to have that trigger, like, oops, there it is. That's what we go with. If it starts with, say, a metal, and some of you should know, or most of you should know what a metal is, such as copper. If it starts with something that is a metal, it is not going to be named in this manner. So that is the very important thing that you need to be able to identify, and that's why having a periodic table out and about when we're doing naming is such an important thing, seeing is that you're asked to name elements on the periodic table and the compounds in which they form. Having your periodic table is so super important. So how do we name them? Well, that we use this binary naming system, and that is using the mono, di, tri, tetra, penta, hexa, hepta, octa, nona, deca. Some of these you will actually already know, such as a triangle has 3 sides. A pentagon has 5. A hexagon has 6. A heptagon has 7. An octagon has 8. Even a tetrahedral, taking one back from geometry, has 4 sides on it. So you will want to have these either written down somewhere or memorized as they are. These are only the 10. We don't use all 10 as all that frequent. Some of them we use more than others. Some of them get used a lot. And it is important to know that we only use these for covalent compounds. Okay? I have bolded, all caps, italicized, underlined. I have 7 exclamation marks. I don't know how much more in a typing way that I can stress and yell about how important it is that we only use these for covalent compounds. Except for a very small number of types of things and examples later on that we will use very, 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 very infrequent. But the major thing is I've seen a lot of students over the years try to use this method for any and all naming. And it's quite stressful on all the parties involved because the student doesn't get to progress through, and the teacher keeps trying to remind students that we only use these prefixes with covalent compounds. How do we name covalent compounds? There's 2 steps. I have tried to simplify this as much as I possibly can. Therefore, when students try to simplify it even more, things usually don't go well. So it is important that we do not try to simplify it any more than I have. I have tried to keep everything into a 2-step process. The first step is to name the element that comes first, which would hopefully make sense. Adding the appropriate prefix that indicates the number of that element. If there is only one of that element, no prefix. That's an important thing. If there is only one of the first element, no prefix. The second step is to name the second element in the formula, changing the ending to IDE, and then adding the appropriate prefix to indicate the number that that element is. Now, changing the ending to IDE can be sometimes tricky because you're changing anywhere between 2 to 4 letters on the element's name. Now, a lot of it comes down to being able to hear yourself say them, and that's an important thing. Just as if you were learning another language, you say these things in class so that you can hear yourself and hear the teacher say these names and say the terms. Well, we have oxide, nitride, sulfide, fluoride. We can also have chloride, bromide, iodide, selenide, which is a little bit weird, but it's selenium with an IDE, carbide, nitride, phosphide. Okay, that was a weird one. Okay, so you have some of them are a little bit more. Now, this IDE ending on the second element is so important. It indicates that you're done naming the compound. You're done with it now. Or it can indicate that the element is a part of a compound that we're just not going to say it, such as fluoride. You know, did you go to the dentist today and swish your fluoride? That's a compound. It's not actually just fluorine or just the ion version of fluorine. It is a compound. That's why it has the IDE aspect of it. We're just not saying what the other part is, and that's where common language and chemistry language don't always match up real nice. And so we have to be careful with that. So let's try some out. For the first one, so we named the first element nitrogen, and there's 2 of them, so we would say dinitrogen. So for the second step, we have 4 oxygen, so we would go tetra is what we would think we would go, but I believe the route that most commonly is taken is tet, and then it is oxide, because it's the ending, so it would be tetroxide. I've seen it written both ways. Both ways are in number of different reference materials that follow the IUPAC rules, so I think it becomes more of a preference. I usually like the A there because then you get the full prefix, especially when we're learning it. So in this next example, we have sulfur, we have 1, and because it's written first, we don't have 1 because by writing sulfur, we are indicating that there is 1 of them there. Therefore, the second element is dioxide because I have 2 oxygen atoms present, dioxide. Now, naming the other way is just the opposite of what we have been doing. So, for phosphorus, we just write a P. Because penta is indicating 5, and we have 5 chlorine, therefore we have that. Disulfur means that I have 2 sulfurs. And in the next one, I have 10 fluorines. The ending of IDE, again, lets us know that the compound is done being named. So it's so nice. We use it when we write it, like we did up here. And then when we're asked to go the other way, it helps us. So, let us name this compound. Cl2O7. The name is... And so the answer to this one is C, because we have 2 chlorines, and hepta is the prefix for 7. Oxide is there. So dichlorine heptaoxide is the name that we have.